Welcome to the solutions to the Regents Physics Dynamics problem set, problems number 37 through 41. You just got done with a Newton's universal law of gravitation lesson, and in this set of problems we applied those concepts to various gravitational situations. Number 37, the moon and the earth are attracted to each other by gravitational force. Does the more massive earth attract the moon with a greater force than the moon attracts the earth? Explain. Well, here I've drawn the earth and the much smaller moon. On the left hand side, let's do the equation to calculate the gravitational attraction of the earth on the moon. It would be big G, that gravitational attraction would be big G, mass of the earth, times the mass of the moon, divided by the distance between the center of the earth to the center of the moon squared. Over here, let's redo the calculation, this time for the gravitational attraction of the moon on the earth. It would be Fg equals big G, mass of the moon, times the mass of the earth, or the distance between the center of the moon and the center of the earth squared. You can clearly see by comparison here that these two equations are ultimately the same. That because of the commutative property of multiplication, it doesn't matter how you order the masses, you're multiplying the masses anyway, and in both cases the distance between the center of the earth and the center of the moon, or the center of the moon and the center of the earth, is the same. These two equations are equal, therefore the earth pulls equally on the moon as the moon pulls on the earth. Oh, by the way, there's a Newton's third law of motion that's Newton's third law of motion, which says that for every action there's an equal and opposite reaction. So we're reminded that those forces should be the same anyway. On to 38. If the earth were twice as massive but remained the same size, what would happen to the value of big G? Well, by inspection, big G is the universal gravitational constant. Big G remains constant no matter what happens to the dimensions or mass of the earth or radius of the earth or any other factor. Big G remains constant. So what happens to the value of big G? Nothing. It remains constant. 39. If the earth were twice as massive but remained the same size, what would happen to the value of little g? Well, from your lesson, you learned that one of the ways to calculate the acceleration due to gravity on a planet was little g, in this case on the earth, equals big G, mass of the earth, over radius of the earth squared. Here they're doubling the mass of the earth. So they're increasing the mass of the earth by a factor of 2. What would this do to little g? Well, little g is the product of big G me over re squared. So by doubling the mass of the earth, you would double the acceleration due to gravity on the earth. Therefore, we would weigh twice as much. Number 40. Charlie Brown has a mass of 70 kilograms and Lucy has a mass of 50 kilograms. Charlie Brown and Lucy are standing 20 meters apart. Lucy looks up and sees Charlie Brown. She feels an attraction. If the attraction is gravitational, find its size. Assume that Charlie Brown and Lucy can be replaced by spherical masses. The reason this last statement is important is so that you can count the 20 meters that they are apart as the distance between their centers. We go ahead and we start with Newton's universal law of gravitation. Fg equals big G m1 m2 over r squared. We sub in the values that we've been given. Big G 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared off the reference table, times Charlie Brown's mass of 70 kilograms times Lucy's mass of 50 kilograms divided by the distance between them, 20 meters, not forgetting to square it. Most common mistake when using this equation is forgetting to square the distance. Go ahead and do that calculation on your calculator, and you should get a 5.84 times 10 to the negative 10th newtons. This force would be essentially negligible when you look at this power of 10 exponent here. Therefore, the attraction poor Lucy feels must be hormonal, not gravitational. Lastly, we have 41. Assume that you have a mass of 50 kilograms and the Earth has a mass as indicated on the New York State reference table. The radius of the Earth is also found in the New York State reference table. A, what's the gravitational force of attraction between you and the Earth? B, what's your weight? C, compare the two values. Well, using Newton's universal law of gravitation, Fg equals big G m1 m2 over r squared. We substitute the values, 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared for big G off the reference table. Your mass of 50 kilograms. Off the reference table, the mass of the Earth, 5.98 times 10 to the 24th kilograms. And then the distance between the center of the Earth to you, which would be at the surface of the Earth, would be 6.37 times 10 to the 6th meters, and we have to remember to square that. Performing this calculation, we get 491 newtons. B, what is your weight? Well, to do this, we do a simple W equals mg calculation. Mass, 50 kilograms, times little g, 9.81 meters per second squared. And performing this calculation, we also get 491 newtons. Remembering that weight is a measure of the force due to gravity on an object, it makes sense that these two values would be the same. You will notice that they are different on your calculator, not rounding to 3 sig figs. And the difference for this is because of sig figs. This 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared, in other words, the value of big G is a 3 sig fig value of that constant. So is the 9.81 meters per second squared value of little g. That also is a 3 sig fig value of little g. If we were to use the perfect absolute values, these two values, even on your calculator, would come out to be perfectly the same. And they should, since weight is a measure of the force due to gravity between two objects, in this particular case between the Earth and you. More work with Newton's universal law of gravitation, as you will do problems 42 and 43 in class tomorrow.